Okay guys, welcome. We're going to do problem 122 in the 14th edition. This is still on chapter 2.9, the dot product. Problem 122. So this is it here. It says determine the components of f. Okay, so here we have this bar. I guess it's leaning against the wall or against the wall and the floor. We have three positions here, A, B, C. And we have a force of 600 newtons acting at point B in this direction. Okay, it's got point D there. So the force F is acting from B to D. We have this this rod from A to C, and we've got all the coordinates over there. Okay. Determine the components of F that act along rod AC and perpendicular to it. So what are the components of this force that act along the rod and also perpendicular to the rod? Point B, this is important, point B is located at the midpoint of the rod. So however long this rod is, B is located at the midpoint. Okay, so I've done a bit of a drawing of it, which we'll look at now, but maybe get your textbook out or try to make a drawing of this figure as well. Okay, so here is my amazing drawing. So here we have the rod. Okay, we've got points A, B, and C, and we've also got this force from B, acting from B to D. The force is 600 Newton, and what we need to do is we want to find what is the component of this force along the rod and perpendicular to it. Okay, so if you want to try this on your own, you can pause the video, then first attempt it, and then you can come back to the video. So remember guys, because we're working in three-dimensional space and we want to find components of a force along a certain direction, immediately we know that we can use the dot product. Okay? So the dot product just simply tells us that if I can get a component of a force in the direction of another line that I choose. So here is my force, and then I want to get the component of that force along this line. Okay? So I guess the first thing that we need to do, because we need this force in vector form, is to convert this into Cartesian vector notation. And how would we do that? Well, the first thing that we need is we would need ultimately, this is what we would need. If we want to convert if we want to convert this force into Cartesian vector form, we need to say F equals the magnitude of F times a unit vector BD. Okay? So that F, what is that F? That is that 600 there, and then UBD as a unit vector from B to D. And then how would we get the unit vector? The unit vector is simply the position vector RBD divided by the magnitude of BD. Then how do we get the position vector RBD? RBD requires us to know what the coordinates of B and D are. Okay? Because remember, what a position vector does is it tells us how to get from one point to another point. How far do I go in the X, the Y, and the Z to move from B to D? So, in order to get RBD, I need the coordinates of D. What are the coordinates of D? Well, if I go 4 in the X and I go 6 in the Y and 0 in the Z. So 4 in the X, 6 in the Y, and 0 in the Z direction. Okay? But now what is B? How would you calculate B? All they say to us is they give us A, they give us C, the coordinates of A and C, and then they say that B is halfway, is at the midpoint. Let's just see exactly what it says. It says B is located at the midpoint of the rod. At the midpoint of the rod. Okay, so can you see that if B is located at the midpoint of this rod, then if I have to move from A to C, right? Let's just say this: my movement from A to B will then be half of my movement from A to C. So how far do I need to move to get from A to C? Well, A, let's just look at A. What are the coordinates of A? 0, 0, 4. Okay, that point there, 0 in the x, 0 in the y, and 4 in the z. And what is C? The coordinates of C are what? Minus 3, 4, and 0. Okay? So how far do I need to move to get from A to C? I need to move from x equals 0 to x equals minus 3. So I have to move minus 3 in the x. And in the y, I need to move from 0 to 4. So I need to move 4 in the y. And then I need to move from plus 4 in the z to 0 in the z. So can you see that if I need to move halfway along the length of this rod, then I would also need to move halfway if I'm looking at these components. So what would B then be in the x direction? It would be minus 1.5, right? Because I have to move halfway in the x direction. I start at x equals 0 and I end at x equals minus 3 if I'm moving along the whole length of this rod. But if I only have to go halfway, I will end up at minus 1.5. Similarly with this one, I need to start at y equals 0, and I need to end at y equals 4 if I move along the whole length. But if I just want to move halfway, then it will be half of that, which is 2. Similarly there would become also 2. Because I need to move, the whole length would be from 4 to 0, halfway would be from 4 to 2. So that is how I determine my coordinate B. Now that I've got B, I can now determine the position vector RBD, which is simply, how do I get from B to D? I need to start at minus 1.5, and I need to end at 4. So can you see I'm moving positive plus 5.5 in the I. I need to start at 2 and end at 6. So plus 4 in the J. I need to start at 2 and end at 0. So it's minus 2 in the K. Meters. Okay? Remember, you can also just say that minus that, that minus that, that minus that. Okay, that's also 100% correct. Then, what's next is we need to, in order to calculate our unit vector, we need the magnitude of our position vector. And the magnitude there, bring out the old trusty calculator, 5.5 squared plus 4 squared plus minus 2 squared equals square root, we get 7,09 meters. Okay? So that length from there to there is 7,09 meters. But really, we're not really looking for that right now. We're looking for UBD. And UBD is then equal to, just trying to get the light in the correct position here, 5.5 over 7.09, okay, plus 4 divided by 7.09, and the J minus 2 divided by 7.09, and the K, and then that equals 5.5 divided by 7.09, that equals 0,77 in the I plus 0,56 j. We have 2 divided by 7.09, 0,28 k. That's my UBD. Now, if I want to convert that force into vector form, then I can just say 600 times UBD. So if I multiply that out, I'm just finishing this off here, 169,2 K, 600 times 0.77 is 462 I, 600 times 0.56 plus 336 J. So there we have our force. We have this force now in Cartesian vector form. The trick was to determine B, okay? And then once we had B, we could get our position vector RBD, and then our unit vector BD, and then multiply that unit vector, and then we end up with this, okay? So now we've that's step one. In order for us to get our component along this line, we also need a vector along this line, right? But what do you recall? What kind of vector do we need along this line in order for us to get the pure component, the projection of this force onto there? It has to be a position vector, a unit vector, correction, a unit vector, okay? So, by the way, I just want to ask you, is the unit vector BC the same as unit vector AC? Yes, they are the same. So technically, if, say now you're doing this problem, and you were not able to find, well, that would kind of defeat the object. But, say now you were not able to find unit vector BC. You can also use unit vector AC because it's exactly the same direction. So if you were able to get F in vector form, you could also use unit vector AC, okay? Because it's the same direction as unit vector BC. But what we're going to do is we're going to calculate unit vector BC, okay? Which is simply R position vector BC divided by the magnitude of BC. So we need to get RBC. So RBC is equal to, what's the coordinates of B? The coordinates of B is minus 1,5, 2, 2. And then C we have there. So we want to move from B to C, from these coordinates to those coordinates. So if I want to move from minus 1.5 to minus 3, I need to go minus 1.5 in the I. I need to move from 2 to 4. 2 to 4. It's plus 2j. I need to move from 2 to 0. Minus 2k meters. The magnitude of RBC is 1.5 squared plus 2 squared plus 2 squared square root, and that is 3.2 meters. By the way, as a check, you can also go and calculate the position vector from A to C and then calculate the magnitude of that, and you will see that it is exactly double that. It's exactly double 3.2, okay? 6.4. Alright? So now we've got our vector and we've got the magnitude. Now we can calculate the unit vector UBC. UBC is minus 1,5 over 3,2 I plus 2 over 3.2 j minus 2 over 3.2 k. So what does this end up being? It's 1.5 divided by 3.2. This equals 0,468 I plus 2 divided by 3.2, 0.625, j minus 0.625k, UBC. By the way, again, if you calculate UAC, you'll see it amounts to exactly the same unit vector. Because a unit vector simply gives you a direction, okay, and the unit is 1. Okay? So now we've got this force in vector form, and we've got a unit vector along this line. And please go to the previous videos to see why does the second vector have to be a unit vector. I just remind you, it's because we don't want to alter the magnitude, because unit vector has a magnitude of 1, and also a unit vector has no units. So if we calculate the dot product with the force vector here and a unit vector, we will simply get the component of that force vector along that line. So let's call it FBC. Remember, I'm not putting a vector line on it, although I'm just going to leave it like that. The magnitude of the component of F along BC, right, along BC, is equal to the dot product of the force dot the unit vector along BC. And that then equals, I'm going to take this force, 462I minus 336J minus 169,2K, and we are going to dot it with this. I'm going to try to fit it in 0.468I plus 0.625J. I'm just going to put down here 0.625K, the dot product. And then what do you recall from the previous exercises is if we're carrying out the dot product using our Cartesian vector notation, it's simply going to be the x components, multiply the x components, plus the multiplication of the y components, plus the multiplication of the z components. So it will equal this, 462 times 0.468 plus minus 336 times 0.625 plus minus 169,2 times minus 0.625. Okay, now I bring out the trusty sharp again, 462 times 0.468 plus minus 336 times 0.65 plus minus 169,2 times minus 0.65 gives me, guys, sorry, I just saw now, I need to include the minus there, so don't worry. There's a minus there, so that needs to be minus. Okay, so if that becomes minus 462 times 0.468 plus minus 336 times 0.625 plus minus 169,2 times minus 0.65, we should get 99.7. Okay? That is what we should be getting. Okay? So now we've got this 99.7. This is the component acting along this direction. Okay? I hope that makes sense. So if we apply a force of F equals 600 along this direction, then what's actually happening is we have a component, a projection of this force along that line of 99.7 Newton. Okay? Now a quick question, if I want to then convert this into Cartesian vector form, what do? I simply take that 99.7 and I multiply it by a unit vector along this line, which could be UAC or it could be UBC. Okay, so this is our parallel force. It's the force along the line. Now, what do we do if we want to calculate the perpendicular force? Okay? Just show you here that if we have, here's the line AC, all right? And here we have that force of 600 Newton, and we've just calculated this parallel component of 99.7, okay? Now if you look here, this force is now the resultant force, and this will be the parallel force. Now this is going to be the perpendicular force. Remember, if we want to break it up into parallel and perpendicular, this will be our vector diagram. So essentially that force plus that force gives us that force, right, if we complete the parallelogram. So one way of doing this, we call this F perpendicular. Remember, I'm only looking at magnitudes now, guys, only looking at magnitudes. We can say, remember that 600 squared is equal to 99.7 squared plus F perpendicular squared, right? This is the Pythagoras. So if I want to solve for perpendicular, I need to go 600 squared minus 99.7 squared square root. Gives me my perpendicular component. So if I do that, 600 squared minus 99.7 squared equals, if I take the root of that, F perpendicular is 592 Newton. Okay? So the magnitude of this force is then 592 Newton. So as I'm applying a force of 600, I'm actually getting the component along the line AC or a line BC is 99.7, and the perpendicular component is equal to 592. Okay, that's the end. Thank you.